This is Mr. Beck Does Your Homework. This is AP Physics homework number 12.2, which deals with double slit interference and thin film interference, two topics that are quite interesting and related to waves. And this is the introduction to the whole homework, so there's some background information that will be useful to review before, say, an exam. What we're going to start with is double slit interference, which is also called point source interference. And from the geometry of the double slit, we will derive Young's equation out of this. So where we start with is we have a screen set up somewhere across the room. We have a barrier here that has a hole and another hole in it, and this is why it's called a double slit. Onto this double slit, what we're going to shine is some laser light. Now, it has to be laser light only because we need these wavelengths to be consistent among each of the different photons of light, or each beam of light. We also need them all to be in phase. So you'll notice that at this point all the crests are going to overlap. So crest, 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 crest. So as this laser light, laser is beautiful for this, hits the double slit, something interesting is going to happen. Each slit then will act as its own point source as the wave comes in. So it's going to be going bump, 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 bump as the wave passes by. What that means is diffraction is going to happen at that point, lead to the waves coming along and spreading out in every direction. But each one of these waves is going to be in phase because it's going to start with a crest or a trough, and so as this one sends its signal, crest, trough, that is going to spread out in these circular waves from each point. Now let's take a look at a point that is exactly in the middle of the slits and draw a line over to where the screen is. It should be pretty obvious that this point is going to be an equal distance from this slit and an equal distance from this slit. Since the 2 points are equidistant since that point is equidistant from both slits, what we see is that if I counted number of wavelengths that are distant from one slit and number of wavelengths that are distant from another, what we should wind up with is an equal number, because we take that length and we divide it by the wavelength, and we'll have some number of wavelengths to get there. But what we see is that since it's an equal distance, and since the wavelengths of course are the same, we wind up with the waves hitting here in phase. So right at this point, the one wave will constructively interfere with the other, and you'll wind up with a larger wave. So if this was a certain brightness and this was a certain brightness, this would actually be twice as bright because they're going to add up there. But if we pick a different point, some distance away from the center, we will find out that this wave and this wave will arrive out of phase. If they arrive out of phase, then what I wind up with is a dark spot because they will destructively interfere. And we could repeat this up along this edge and down along this edge, and what we'll find is we'll have bright, dark, and so on. So we'll have this pattern of bright and dark fringes as we go either way on the screen. Also, if we were to count the number of wavelengths from this screen back to the slit, we'd see that we get we'll just count, we'll count crests. 1, 2, 3, 4, 5, 6, 7, 8, 9 crests there. And here it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 crests. Or 9.5 actually. So we wind up with 9.5 versus 10. So what happens is the distance here and the distance here are off by 1/2 of a wavelength. And if we actually drew a line from here to here, we could make ourselves a little triangle here, which shows us that this distance and this distance here, that we would have this little distance representing 1/2 wavelength difference in the length between this line and this line. And that's going to be key to deriving this equation. If we continue this to a point still further out, now we will have this wave and this wave meeting crest to crest again, which would again be that next bright spot. So we had a bright in the middle, and then a dark, and then a bright, where we had equal path length being this. At this point, the difference in the distance was going to be a 1/2 wavelength difference, and at this point, the difference in the distance, the path length difference, was a full wavelength. So again, if we drew that little triangle here, we would see that this should be one full wavelength now as opposed to a half wavelength before. So this distance and this distance would be equal, and then we have that one extra wave going in there. So now we're going to simplify this picture and just take a look at the geometry. This distance from the slits to the screen, this distance here, we are going to call L. This distance this is kind of an average distance from the slits to the screen up at this point where we're going to have a bright or a dark or whatever. That is what I'm going to call L prime. The distance that from the middle, from the center bright fringe is what they'll usually call it, the distance from the center to here, whatever that distance is going to be called X. Now we also had this little triangle here that we drew where this was the difference in length from here to here versus here to here. So this little difference in length is going to be represented by some number of wavelengths, and we're going to write that as m lambda, where m is some number and lambda is wavelengths. The difference between the distance between the slits we are going to represent as d. So you can see by some geometry here that I've got a d and an m and a lambda. This is going to form just about a right angle. This is going to form definitely a right angle. So I've got two things that I can write here. One is dealing with this angle right here. I know that I can write that distance times the sine of that angle is going to equal some number of wavelengths. So d sine theta equals m lambda is a always good representation, even though it's ever so slightly off because that might not be exactly a right angle. It's close enough that this one will be good to, 1 part in 1,000, who knows. But so this distance between the slits times the sine of this angle is going to be m times lambda, and by a little bit of geometry you can see that this angle is pretty much going to be this angle. So if I want to know what angle I'm going to find the bright fringe over here, well, if it's one wavelength, then I will find the bright fringe out there. The other thing I can do is compare this triangle with this triangle, and I can get some ratios. So the ratios I can see is that d is to m lambda as L prime is to x, or x is to L prime as m lambda is to d. And when I put those together, what I get is x equals m times lambda times L prime over d. But I won't always know L prime, so for small angles, since L prime and L are pretty much the same, are very close, what I'm going to do instead is I am going to say that x equals almost m times lambda times just L over d. And that is Young's equation. X, the distance from the center to the whatever this point is going to be some number of wavelengths times L, which is this, which is almost that, divided by d, the distance between the slits. So m lambda over d is x to L, m lambda over d is x to L prime, or almost L. So this works for small angles, angles less than, say, about 7 degrees, 7, 8 degrees. This is going to be well within 1%. So what I'm going to see actually when I put it all together is a pattern where in the center it's going to be bright. Let this represent brightness and darkness and brightness and darkness. In the center it'll be bright. This is of course a different pattern, but some distance away it will be dark. Some further distance away it'll be bright again. Some further distance away it's going to be dark again. Now each one of these brights and darks represents a very specific distance that is off by some multiple of wavelengths. So I know that at the center point I have an m in x equals m lambda L over d of 0. The first dark I'm going to have an m equal to 1/2. The first bright away from the center bright fringe is going to be an m equals 1. The second dark is going to give me an m equals 1.5. And the second bright is going to give me an m equals 2. and then the second dark is going to be at 2.5. So these are values of m. So I've got 0, 1/2, 1, 1.5, 2, 2.5. A couple things to notice are that the darks are always going to be multiples of half. The second dark happens at 1.5, so it comes before the second bright. So be careful if it says the seventh dark, that would be at 6.5 for a value of m. The other thing to notice is that this distance between bright and bright is going to be the same thing as this distance between dark and dark is going to be the same thing as this distance from bright to bright. So you know that once you figure out that distance, it's going to be the same regardless of, what number you're going to. So from the third dark to the fourth dark would be the same as from the second bright to the first bright, that sort of thing. So that should set you up for Young's equation. Let's see, the first dark is going to be at 1/2. The first bright is going to be at 1. The second dark is going to be at, D-A-R-K, is going to be at 1.5. The second bright is going to be at 2, and so on. So I get dark, 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 and I get bright, bright.